big thank you for staying this long because it's late. So maybe before I begin, how many of you are technical? Hands up. Great. How many of you have had experience with FPGAs? Yeah, cool. So we're good to go. So the topic of the presentation is FPGA accelerated packet capture, or how to do it efficiently on SoC FPGA chips, like for example DE0 Nano SOC, which I used for this project. So here you can see the outline. It's not really long. Who am I? First of all, I'm a developer that's currently doing 5G stuff, L1 layer at Tietoevry, but I'm contracted for Intel, so it's like a word of contracting. I did some work at Samsung. I also did GPGPU with BeagleBone organization on GPGPU acceleration during Google Summer of Code. I also recently graduated. I'm also leading a team of skilled engineers at Tieto. And that's what I do. I do some sports and basically try to smile. Problem statement. So, first of all, why should we even care about offloading anything like packet capturing to hardware? Is it sustainable? Is it feasible? So the answer is it depends. Like everything you should measure, but I believe that as you'll see in a moment, or everyone already knows, that we have a rise in IoT devices. Recently, we've been having more and more devices that are equipped with FPGAs. So and SoCs, like there is one that utilizes Cortex M4A, I think, and has an eFPGA. So this is growing. So that's maybe a good time to jump on the wagon. You can see the numbers here that basically the data number is, the amount of data is rising, the IoT, the number of IoT devices is also rising, but we all know that. So, and basically there is not many good resources on how to accelerate, want to accelerate, and when to accelerate. So this talk aims to fill that hole a little bit. So here you can see three main, let's say, types of devices that you can accelerate on, especially network processing. So for the CPU world, we have DPDK. I don't know how many of you have some experience with that. Yeah, it's a niche topic, but So as for GPU, we have two state-of-the-art accelerators, Packet Shader and APU-Net. I will link some resources later. And for the FPGAs, we currently have smart NICs on the market, which are smart network interface cards that usually use a kind of ASIC that's application-specific integrated circuit. And a little bit of FlexRun, that's the project I'm working on, and we're using DPDK at Intel. So how embedded networking is different from regular one? We use less power-hungry protocols, simpler ones like MQTT or CoAP. We also have less powerful hardware and software running on the chips. And we usually don't have the possibility to use a full-blown Linux distribution. Usually it's some kind of RTOS or non-real-time operating system like TOC. I don't know if you know it, but it has been rising in popularity. But here we'll focus on embedded networking on Linux. So yeah, that's basically that's my ugly diagram. I made it by myself. So as you can see, that's like a very overly simple diagram of how networking is done in Linux. So we get a packet on Ethernet network interface card, then there is a ring buffer, and the packet is read when the interrupt fires. The driver gets the packet, and then the NAPI, which stands for New API in Linux net systems, starts to work. And where I hooked in is on the BPF virtual machine, eBPF. So there I hook in a small XDP program that redirects the packet to the FPGA. So that's basically how it works from the networking side. Yeah, so here I've been using Intel Avalon MM protocol or Altera Avalon, depends. And most importantly, what I want you to take away from this is that I use bursting capabilities because it makes the processing much more efficient. So how many of you know what bursting is, maybe? Yeah, okay, so it's just delivering data in batches so that it's just more efficient, not processing one by one and wasting cycles. So yeah, as I mentioned already, there is not much relevant work yet, so this might be an opportunity to dig into it. Most of the knowledge I've been searching for is ephemeral, and the buzz factor is just rising as not many people are taking up the mantle anymore, and they want to do easier things. So that's why we need good documentation and yeah, just efforts like this, I believe. And if you are into network acceleration, then you probably know about RDMA, which stands for Remote Direct Memory Access. And it's used extensively on SmartNICs. So yeah. Here you have some 3 state-of-the-art works that I've been investigating to see how much traction is there on the topic. I won't go into details. You can look it up later in the presentation slides, but spoiler alert, the offloading in all 3 of these cases is efficient. So yeah, let's maybe go to the system overview. So as you can see in the diagram, we have 3 main boxes. So we have the Linux kernel, the user space, and the FPGA part. Just a quick reminder, in the SOC that we're using, we have the ARM CPU on the same chip that the FPGA is, so we don't have relative delays, not really big. So, I mean, there are some, but let's skip them for now. And in the diagram, you can see that the packet can go either through the eBPF VM subsystem and return with pass, then go through the entire net subsystem and be processed and then be delivered to the user. Then the user can take the packet out using, for example, TCP dump or some other capturing program and save the result in a pickup file. In my case, I decided to hack the driver, and I returned the XDP capture return code, which I added, and then the FPGA kicks in, and basically what it does is it's just a data moving machine, which seems to be pretty simple, but in turn turned to be out not that simple. I'll just go into more details in a while. So yeah, some modifications. Since I was using Intel Quartus IDE, I had to integrate it with the proprietary toolchain here and add some device tree entries. First one is for the pre-reserved buffer in the RAM that is shared between the FPGA and the kernel, so the kernel doesn't work on this memory. And I also added the device on the right. The test environment was pretty simple. I just had a host PC which was tethered via an Ethernet cable to the target board, which is running, as you can see, D0 Nano SoC and two flavors of Linux kernel and bootloader, which are especially patched for this board. And the root file system was not built by Yocto, surprised, it was built by Buildroot. But it might be built by Yocto, so we'll see. The test procedure was pretty simple, so we just can set the parameters, then recompile it, load the XDP program, start the test, which in my case was just pinging with some kind of interval between consecutive packets and then capturing the tracing output. And finally, calculating the deltas that it took to process the packets, starting from their entry to the kernel, finishing with the time when they were when the FPGA returned that the processing is done. So yeah, here you can see the driver patch, which actually is not that complex. On the left, all the code will be available in the. It's available on GitHub, but it also is available the presentation online. So I won't go into many details here, but on the left there is driver initialization, and on the right we have STM-MAC XDP run prog, which is the hook that's run whenever XDP is triggered on the, in the kernel, basically. So whenever a packet comes, the XDP program runs, and in this case, we fall into case 5, which stands for XDP FPGA capture that I added, and we did some. We pass the packet to the kernel, to the FPGA, I'm sorry. So here you can see the read controller module. As you can see, it's circled in green on the right, and I mean on the left from your perspective. And what it does, it basically loads the data from a address in that was passed by the kernel, and it queues the packet to the FIFO. the write control module is slightly more complex, as it has to manage the delays that might be, the stalls and delays that might be occurring on the receiving end. So we had to add first ring buffer capabilities to achieve the possibility to be capturing the data continuously, because obviously the buffer is finite, so we couldn't, I mean, if we had so much RAM that we could avoid to not have it, then the implementation would be much, much easier. But I will get into it later. And what it also does is stamping the pickup, adding timestamps and pickup headers to the data. So yeah. Also, as I mentioned, stalling and delays might be an issue whenever you have a receiving agent in this case. So there is a special construct that's called a skid buffer, and it's basically a smart register that just knows when to hold the value and when to pass it further down the pipeline. So simulation, of course, had to be done. Model sim was used for quick and dirty simulating and making sure that everything works as intended, and Signal Tab was used for as a onboard hardware logic analyzer. So maybe more interesting part of the talk, give me some results. So one most obvious conclusion is that you increase your processing, you increase your clock frequency, you get more data being crunched. And this is best visible here, that probably the one most important graph that you should remember from this presentation is this one, where we can see that the lines are going down, which means that the greater the packet size, the greater the frequency and burst length, the less time it takes for us to compute to pass the byte through the capturing module. So, and you can see that for small values of packet sizes, the overheads are really visible. And yeah, let me jump back to the previous one. So this one just focuses on the doubling of burst length. So whenever we double the burst length, we get a 33% increase in processing speed. So here we have, on the edge of the slide, you have burst length of 4 words, and closer to the middle is one of 16 words. So even here, you can see that the overhead for small packages is visible. And yeah, and as you can see, for 1 kilobyte packet size, the time gets halved, for example. Yeah. One surprise, power consumption remained steady. So this was a big surprise to me when I first stumbled upon it. Apparently, later I discovered that I've been not using any low power and sleep states in the CPU. So and basically it seems like even though there was no code on the FPGA running, the consumption was the same as with FPGA processing packets at, for example, 200 megahertz. So one obvious thing, you turn off the Ethernet module, you you lose some power consumption, so you gain some cycles there. And this also might have been caused by the fact that, well, this is an embedded device and it wasn't flooded with packets all the time. So the logic, even though it was processing on 200 megahertz, for example, it only did it for a fraction of the total running time, right? But then we would need to check if the SDRAM, for example, would handle such a throughput, etc. So now we go into more details. Yeah, in terms of resource utilization, it's pretty lightweight. I think it might be not visible here, but it just utilizes 3,700 logic ALMs, and most of this is taken by the auto-generated interconnects. And why they have to use interconnects, I will go into details in just a little bit, because this was the main hurdle that I had faced with this project. So yeah, maybe before conclusions. So the main issue here was that I could not turn on the FPGA to SDRAM bridge, which had 256 bits of RAM of bus width. I'm sorry, and instead of that, I had to resort to using two AXI buses. That one was for reading, one for writing, and this caused me much pain. And apparently, Cyclone V or Cyclone 5, apart from being unsupported in newest version of Quartus, which I painfully experienced during this project, it also doesn't support the FPGA to SDRAM, no matter what you do. If you set the registers in the FPGA and some other things. So this is one warning for you. If you want to go down that rabbit hole, don't waste your life. So yeah, some conclusions. Maybe yeah, let's not drag it over, but first of all, as I said, your mileage may vary, but it can be efficient if you know when to accelerate and what to accelerate and how. Yeah, of course, this talk is to tell you a little bit how. So one important thing is that the higher you ramp up your clock, the wider your buses, the longer your bursts are to a reasonable limit, the more the less time you spend in I'm sorry, I got somewhere else. So one more time. I showed you that you go up with frequency, bus width, and burst length, you get more throughput and better performance. That's basically it. And take bigger packets. So you're limited usually by maximum transmission unit, which usually it's 1,500, if I'm not wrong. And so I checked up to 1 kilo. And one important thing, this is a trivia maybe, but I compared it with the baseline. So I checked how it fares against the regular in-kernel processing on this particular board. And it seems like I was getting 16 times to 100 times less times spent in processing. But remember that kernel did all the filtering, etc. So it must be taken with a grain of salt. Also, my company is going to, Tietoevry thinks to port this to more beefy FPGAs to see how it fares on servers. And of course, this is aligned with the goals of carbon-aware SDK and Green Software Foundation, which aim to reduce the, let's say, ungreenness of the business that we're working in sometimes. Future work. So what could be done here? So first of all, stress testing, packet floods, etc. If the board burns, then yeah, we've tested it to the limit. Of course, initially this was aimed to be TCP dump-like, but it turned out that implementing some features was just too time-consuming, and I didn't have enough time to do it. And of course, I was bogged down by issues like not functioning bus or hanging bus, even though I was using proper addressing and everything, because it turned out that Altera or Intel had a bug in Quartus 19.3 where the interconnect would be generated wrong, so I was addressing in bytes and they still were addressing in words, so the bus hanged and I didn't know why. Axie showed it perfectly, so one more reason to use Axie, not Avalon. And I've been talking with Antmicro company about utilizing their Antmicro video board that has open toolchain, open hardware, but they're still using Zing 7000, so this is still some kind of vendor lock-in, but a sponsor, they released also a open source toolchain for Xilinx devices that's called Enclastra. So this might work. Of course, if there is some effort to port it to RISC-V, I would be very happy to. So tentative plan of action is to avoid vendor lock-in and some troubles with, for example, not working buses and etc. Or port it to RISC-V and be your own, let's say, maintainer. So some acknowledgements. This work couldn't have been done with help of my colleague Sebastian, who is an expert in FPGAs. And basically, he told me why the bus was hanging. And we had some hours of contemplation why life has to be so hard sometimes with these issues. Matthias Becker for constructive criticism and support. Shimon, who is my brother, who encouraged me to come here and fight the imposter syndrome that sometimes kicks in. And of course, to all of you for teaching me how to do it, showing me this amazing topic, and I think that's almost all. I'll leave some links. I have written a paper on this. It's available on my website, and if you want to follow this rabbit hole, then you may. There is one good resource that I recommend. Is this second link from the bottom. It's concerned with DE10. So it's slightly different, but it's still a good attempt at putting it all together. So call to action time. What do you think? Do you think it is a good area of research? Should it be pursued, or is it important? And let's discuss it. So I think that's thanks from me.
Hi, I just did a quick in-my-head review of a Linux driver. You would probably be better off using the DMA allocator for your memory area, because that will give you both the virtual and physical address of the page of memory and will allow you to do cache maintenance on it. Because otherwise, I think you were doing probably something which wasn't very cacheable, and your memory read performance will go up if the CPU can cache the memory.
Yeah, I think that in this case, what I aimed for was to have a contiguous buffer, which would be just read once by the. FPGA reads and writes to the physical memory there, and the system just has to go through it once, I think, when it's just collecting the pickup file. This might be.
It would certainly be if you're using a lot of memory, and the API is fairly easy to use and will integrate with reserved memory.
Okay, cool.
So you probably want to have a quick look at that, and it might just improve your the code and not have to worry about the virtual to physical mappings that can go horribly wrong in some systems. I have systems where the coherent memory does not live in the same place as the non-coherent. It's like, it makes life a lot difficult.
Okay, thanks for that.
Yeah, thank you. One question with regards to why. Like, why would I put the Ethernet into CPU rather than into FPGA itself and do this stuff out there and then produce the output? And when we do so, like, is it just a simplifying thing so that the lesser knowledge needed to enter this stuff or something like that?
Good question. Here, I decided basically to use what's available. So if you were to do it, let's say, more efficiently, then of course having an FPGA which would be offloading, for example, doing a T and just sending some data, this would be a hardware solution. But I think this would be much feasible. So in this case, this project could be reused. For example, the hardware part, reused, just ditch the driver in this case. But it would require a special board, which in this case was not really feasible to me. So I just took what I have and I tried to make the most of it. So, but I totally agree. The best way to do it more efficiently would be, as you said, FPGA and just teeing the output through the capturing program. Then it could be accessed from the user space, regardless of what is being done in the kernel networking processing. So yeah, I totally agree.
So I was wondering, how does it affect latency? Because you have to do that extra copy between the devices, so from the FPGA back to the CPU to actually use it.
Yeah. So again, that's, as I said, your mileage may vary, so that's important to measure. In this case, we don't really care about the performance here because we don't put we care about the performance, but we're not interested in getting these packets from the capture place. They don't need to be real time. So in terms of processing via kernel, they will still go through it, and they will be just captured, let's say, in parallel. So that's where the FPGA, the separate FPGA solution is probably winning here. So yeah. And also, we want to measure this, right? So I had some experiments, but this was with GPU computing, where actually it's like until you go for big data, the overhead of transferring between CPU and GPU is usually quite big. So, of course, depends on the hardware, architecture, and all other kinds of things. So, yeah.
Let me get one question in, and then we'll let you back. You showed at one point the steps of kind of setting up the system, and you had to download the program with this IP link, etc.
Yeah.
Is that plumbing that you had to build yourself, or this already exists? Just send an object file to my network card. This is normal plumbing, or you created this plumbing?
Let me go back because I don't remember. Sorry.
And you have one with numbers.
Yeah. I'll just go back there. This one, right?
This one, yeah. So this number 3.
Yeah.
This in order to do this, this already exists in the kernel, or you had to create this?
So this is in the kernel. It's using the XDP BPF capability. So I basically use it as a trampoline to just push the code where I want to. And that's why I didn't do it initially with the separate FPGA as well, because I wanted to leave a gate for possible eBPF pre-filtering, because it's so powerful that it might just capture, for example, packets that are, I don't know, some specialized protocol only. And we might not want to do it in hardware as it is blazingly fast. But for capturing and saving, then this solution bypassing the kernel entirely might be more useful. So this is all in the kernel already. You just need to enable eBPF and just install the iptools2 package and write a simple program that and compile it using BCC compiler tools. Okay, like this.
Thank you.
Yeah, thanks.
Yeah, in continuation of my first question, so like why? I would think then, okay, so I would probably have a kind of a workload when I have the setup pre-installed and I cannot interrogate somewhere between the Ethernet cable, my media, and the machine, then this particular solution, and you referring to the Avalon bus or the interconnection between ARM and ARM core and FPGA itself. So I would think of, okay, then to offload that, I would need to FPGA being somewhere around, and for a real system, I would have some FPGA installed in PCI Express slot. Then it will be a latency that you neglected in the first case. But then the DMA solution would be perfectly well here, and it will be brilliant, to-go way with the FPGA here. The other way around is you mentioned the SDRAM slots, and there is actually a project, Mr. FPGA, for the old retro gaming, and they have introduced a SRAM extension board for the Altera boards, so we can use SRAM. It is much simpler. You don't have to mess around with DDR initialization process. It's a cabal thing, kind of thing. So yeah, it's probably a way to go. Thank you.
Thanks. So just maybe building on top of that, the RDMA actually, as you said, just DMA. Okay, but. Yeah, okay. I thought that, so you would like to have the FPGA on a NIC slot and just to, yeah, so we're talking about some bigger workloads here, right? Yeah. Okay, so good idea. That's all I can say about this.
All right. Anyone? Oh, you want to do? We're going to fight over who's going to ask the last question. Go ahead.
It will be a really small one. The protocols, you said it's TCP.
Yeah.
What's about ICMP, because it's relative protocol to TCP? You can't do the things without that. And what's the level of capture? Is it TCP capturing, or you go to the Ethernet frames? What are you doing? And towards to Ethernet, you said it's MTU 1.5, the upper limit. Can we do the jumbo frames with it?
Yeah, sure. You can do whatever the size would you like to. I limited it to 1 kilo for now. But obviously, yeah, you could capture whatever size you want. This is also a good point for more measurements and better metrics in this project. Yeah, I think this answers. You capture raw data that's coming on the link. That's basically what you do here. So yeah.
All right, then I'm going to use my power as a session host to ask the last question, and then we'll thank you again. The limitation that you had with the DMA and the DRAM. So before, we all feel bad about all FPGA. So it's about the chip that you had, like it was an older chip, so a newer chip solved the problem, or it's what? Who messed that up for you? Who
Maintainers.
Can we blame? Okay,
Maintainers
software maintainers
are to blame, and first of all, poor documentation, as I said, or no documentation. I mean, the resources that are scattered around and not up to date. That happens, and of course, they write one thing in the spec, enable this and this and that register. I did it. I tried it on several versions of software. Doesn't work on firmware. So yeah, seems like that's why I believe that trusting vendors on especially not latest and expensive boards might be a shot in the foot. So,
okay.
So yeah.
Okay. So a different chip would not have had the problem, or
I think yeah.
More likely. Okay. Beautiful. So thank you, Jakub, for everything.